All right, this video is going to be about rotational motion, which is chapter 10, which is different than circular motion. So we're going to have things that are rotating around. And I have to say, I'm at home and my family's all around, so if you hear some noise in the background and my kids playing, that's just how it's going to be. This is all about chapter 10, which is about rotation. So first I want to start off by defining a few things here and talk about the difference between translation and circular motion, and then rotation, which is where we're going to be. So translation is pretty basic. This is the simple motion we've been doing for a while, and this is when something is moving along and it's got some position, like say x, and it's got some velocity. Maybe it's got an acceleration. We're just trying to see where it is. Maybe there's an initial position right there, something like that. So that's just things that are moving, mostly in a straight line. They could potentially turn if they wanted to, turn a little bit. When things start to turn more and more, then we get into circular motion. So you might have a car. Here's the view from the top of a car that's going around and around in a circle. So there's a center point, and at any point it's got some sort of tangential velocity. And then we also talked about a centripetal acceleration, which is pointed towards the center of a circle. So this is something that's going around and around and around. And rotational motion is going to be when something is rotating, obviously. So let's say you had a cylinder or something, and I'm going to draw this dotted line as an axis of rotation. Axis of rotation. And it's going to be rotating around. Ooh, that wasn't a very good job of doing an arrow like that. So it's going to be something that's rotating around and spinning around an axis of rotation. So just like I had my watermelon plate here that's spinning around and around. So I could have this watermelon plate do translation. I could have it do circular motion if I moved it around and around like this. And then I could have it do rotational motion. Of course, I could combine a lot of those together. I could have it going in a circle while it's rotating, while it's moving across the screen. Okay, anyways, maybe not that well. All right, let's get into a couple things here. Let's talk about variables. I'll just move this away. So we have translational variables, which should be pretty familiar for you all. And those are things like position, which we mark as x, displacement, delta x, velocity, which is the time derivative of the displacement for instantaneous velocity. We have average velocity, which is a change in position divided by change in time. And then we also have acceleration, which is the time derivative of velocity, and we have average acceleration, which is change in velocity divided by change in time. So let's see, we're going to change these all, and we're going to have rotational or angular equivalents to these ones. Rotational angular equivalents. First of all, when we have something that's rotating around, we can talk about its position. We also have to define a zero spot. So if I define my zero spot as right here, and then I start to rotate this thing around, I can figure out where its position is relative to that spot. And that position, we're still going to call it position, is going to be an angle relative to a starting spot. So we're going to have position is theta. We can still have an angular displacement. An angular displacement, which is going to be a delta theta, which could be like a theta 1 minus theta 0 or something like that. So that's going to be if I started in this position right here, and then we rotated to this position. So if I start in one position and I end in another position, maybe we can have a reference point of something. Then I can have a change, oops, probably should be from the middle here, a change in a angle like that, a change in position. That's going to be angular displacement. We can go from velocity, and then we can have an angular velocity. So of course it's going to be equal to, there's going to be a couple different kinds. We're going to have an average angular velocity, so that's going to be your displacement, angular displacement divided by time. And we're going to have an instantaneous angular velocity, which is going to be d theta dt. The variable for this is a lowercase omega. It looks like a w, but it's not a w. It's a lowercase omega. And then this is going to be omega average, like that. So that's average angular velocity and instantaneous angular velocity. And then what else do we have? We have angular acceleration. Angular acceleration. And that's going to be, in the instantaneous case, the time derivative of angular velocity. And it's also going to be, in the average case, the change in the angular velocity divided by time. And the variable that we use for this is a lowercase alpha. So there's an alpha. So that is the angular acceleration. So what do these things really mean? Angular velocity seems pretty reasonable. How fast is this plate rotating? And then is that rotation getting faster and faster and faster and faster and faster? Is that rotation getting slower and slower and slower and slower? So that's going to be angular acceleration. So we can have angular velocity, perhaps at a constant speed. We could have it speeding up, going faster and faster and faster and faster and faster. We can have it's going slower and so forth. I also want to talk to you about whether these things are vectors or not. So let's come over here and let's say, are these things vectors? Now, of course, over here, we have displacement, that's a vector, velocity is a vector, and acceleration is a vector too. On this side over here, I'm just going to group this together for angular velocity. Angular velocity is definitely, yes, it is a vector. It has a direction associated with it. So it matters whether we're rotating one way or the other way. It matters. The direction is going to be pretty interesting. So the direction is not going to be clockwise or counterclockwise or left or right. To find the direction, we have to have a right-hand rule. You have to have a right-hand rule. So to find the direction, let's say that my plate is rotating. I'm going to do it this way so it'll be easier. It's rotating this way. So from your view, from this top view, it's rotating counterclockwise. So how do we find the direction of the angular velocity? So what we're going to do is we're going to take your right hand, you're going to wrap your fingers around in the direction that the motion is going, and your thumb is going to point in the direction of the angular velocity. So when this plate is rotating this way, then we're going to have the angular velocity have a direction is up, so out of the page. If it's going this way, then we're going to have the direction of the angular velocity be a little bit down. Can you be a little quieter, please, over there? Excuse me. Okay, sorry, I had some background noise there. So we have, if it's rotating this way, then the angular velocity is going to be going down. So my thumb's going down, so it'll be into the page. It's strange to think about that. It's rotating this way and it's going down. So that's how it goes. Is angular acceleration a vector? It turns out that yes, it is a vector. Now, how do you describe the direction of that? Well, it's going to be determining on whether this thing is speeding up or slowing down and what the direction is. So we have rotating in this direction. Then let's actually go the other way. Let's say we're rotating in this direction. No, sorry, backwards, this way. We're rotating in this direction, and the angular velocity is up. If it's increasing its speed and getting faster and faster and faster in the same direction, then the angular acceleration is also going to be up. So if my angular velocity and my angular acceleration are in the same direction, then I'm going to have them be increasing speed. Let me go back to remind you about translation. If my velocity and my acceleration are in the same direction, then I'm going to be speeding up. If my velocity and my acceleration are in opposite directions, then I'm going to be slowing down. So same thing with the angular things over here. If I'm going this way and I'm going faster and faster and faster and faster and faster, then they're both going to be in the up direction. If I'm going this way but I'm slowing down, then my angular velocity is up and my angular acceleration is down. So that's that. What's strange though is it turns out that angular displacement is not a vector, at least in 2 dimensions. And there's some interesting reasons for that, which I can perhaps point you in a different direction if we want to talk about that. So angular displacement, it turns out, is not a vector. Okay, let's go on and talk about a few more things here. I wanted to talk about, let's get all this into the picture here. I'm going to talk about equations of motion. What we have are translational equations, and we also have some rotational or angular equations that are going to be equivalent to this. So for translational motion, if we're trying to find the position of something, we can use this equation. If we're trying to find the velocity, we can use this equation. If we're relating velocities and accelerations and displacements without time, we can use this equation. So there's going to be rotational or angular analogs to these. So this one I can just replace all the variables over here with angular variables. So it's going to look like this. We're going to have the position is going to be 1/2 angular acceleration times time squared. Now time is just time. There's no angular equivalent to time. It's just time. Plus initial angular velocity times time plus initial position. Down here, I can have angular velocity is equal to angular acceleration times time plus my initial velocity. And down here, I can have angular velocity squared is going to be initial angular velocity squared plus 2 times my angular acceleration times my change in position. This one, by the way, is also how we get angular acceleration is change in angular speed divided by time. So that's final minus initial divided by time. So you can use these just like you use these. If you happen to know the angular acceleration and the initial velocity and the time, you can figure out how far something's rotated, how fast it's going in a particular time, and you can do all sorts of things. So there's practice problems like this as well that you can try out. And then I want to talk about, the last thing is how we get from translational variables to rotational variables. And so if we have something that's rotating around and around like the plate over here, and I want to just pick a spot over here, if this thing has a particular angular velocity, and maybe it has some sort of angular acceleration as well, which could be speeding up or it could be slowing down, I want to be able to relate a few things here. First of all, there's going to be some sort of tangential velocity for any particular spot that you pick here. If I pick a different spot, it's going to have a different tangential velocity. And I can relate the magnitude of these things, the magnitude of this velocity with the magnitude of this velocity, or the magnitude of this velocity times the magnitude of this velocity. And it's going to be related to how far away you are, the radius right there. And you can see that the further away you are from the center, the faster you're going to be going. So I can relate my translational velocity to my angular velocity by putting r inside of there. I can do the same thing for the position and for the acceleration. For the angular acceleration, I'm going to have my, so if this thing is speeding up, then this position, this spot right here is actually getting faster and faster and faster as well. So I can have a translational acceleration is going to be r times this. Hang on to this for a sec because there's going to be something going to add in. And then my, when I have a translational position of sorts that's related to, so this is going to be equal to r theta over here. What's my translational position? So if I've gone through an angle theta like that, then what I've traced out here is actually an arc length. So that length right there is going to be an arc length, which is going to be s. That's the variable we use for arc length. Arc length. So that's going to be s equals r theta like that. A few things. Let's come up here and I want to just talk about units real quick. So the units for velocity are meters per second, and then the units for radius right here are meters. So that means that my units for my angular speed have to be 1/seconds, which is a strange thing. If you think about 1/seconds, that's actually the same unit as a frequency. So angular speed has the same units as a frequency. So sometimes you'll see omega actually used as a frequency. You might be tempted to write something like radians per second up here, which is totally fine to write as well. But it turns out that radians aren't actually really things. It's a unitless quantity. There's no actual quantity to a radian. So you can just call it radians per second, or you can just call it per second. One other thing down here before I get to the period of rotation is I wanted to talk to you about there's a radial or a centripetal acceleration as well. So when we talk about something moving, maybe we'll bring this back over, when we talk about something moving around and around in a circle, there's a radial or a tangential, a radial or centripetal acceleration. So let's pick another point right here. And this point right here is going to be moving this way, but it's also going to be accelerating towards the center of the circle. So there's a centripetal acceleration. And the way that we can relate those together, if you remember that centripetal acceleration is v squared over r. And if we substitute this equation in, that's also going to be r times omega squared. So this is a way that we can do the centripetal or radial acceleration. And then last thing is period of rotation. This is sometimes something that we want to do. That's t, how much time does it take for something to rotate all the way around? The period of rotation is always going to be, it's really a distance divided by a velocity. So this is like distance equals speed times time rearranged. If you want to do distance equals speed times time, or speed times time other way around, then we can get this out of it. We can also relate this to angular quantities by saying 2 pi over omega like that. And then lastly, you can see why this is sometimes called a frequency, because it's an angular frequency. So if I rearrange this equation, I can get omega is 2 pi over t, big T. If you think about, we've had some equations in the past where related frequency is 1 over the period. So sometimes this is called an angular frequency when you stick in that extra 2 pi in the top there. That's called angular frequency. So that's why this is related to this up here. So there we have just the basics for rotation and variables and positions and displacements, velocities, accelerations. Equations to use over here. How do you get between translational and angular, and then period of rotation related to frequency. Try out practice problems in the book, try out homework problems, and hopefully this will work for you.